Welcome to the final section of these notes, section 4.4, where we talk about Fourier series. Our goal is to apply projections to find the closest approximation for function f in a subspace W of a vector space of functions. All right, so we're going to use the same idea that projections onto the subspace are the closest element of the subspace to our original element. We're going to apply it to functions this time. In this section, we'll translate the idea of least squares to the vector space of functions. We'll consider the vector space CAB, that's functions from the interval AB into R, as before with F, but the C means continuous, so F is continuous. Part of the reason we want it to be continuous is that we're going to define an inner product that has an integral in it, so integral from A to B of f of x times g of x dx. All right, so the following theorem is simply theorem 4.2.5 applied to this inner product space. Let f be any function in CAB and let w be any finite dimensional subspace of CAB, then the function g and w that minimizes the distance to f is the projection onto w of f. All right, that's the closest function in W to f. All right, so this function is called the least square approximation of f in W. All right, again, this, if you apply it to the same thing, you get squares. It's the same reason why we use least squares approximation, that word, before we're using it here as well. Although this construction applies only to any AB and to any finite dimensional subspace of W. So you could look at just a set of polynomial, could be your W, AB could be 0, 1. You could apply it to any combination. We want to get Fourier series, and so we're going to concentrate on one specific case. To get Fourier series, we'll consider a specific case. We'll be looking at the vector space C0 to 2 pi and the subspace W of trigonometric polynomials of degree n. So let's see. Trigonometric polynomials. A trigonometric polynomial is a function of the form t of x is, it's going to be a sum of cosines and sines. So it's going to be a0 plus a1 cos of x plus b1 sine of x. And we'll go up to an, and we're going to multiply x by n and bn sine of nx. All right, so this is called a trigonometric polynomial. Notice that instead of putting powers, we're going to put indices here, but of course those were related by trigonality. The degree of t of x is the biggest n, so that either an or bn is not 0. All right, so we want to consider least square approximation on this subspace of trigonometric polynomials of degree n or less. Right, so for that we need an orthogonal basis. It turns out we already have one, so proposition 4.4.2 in C0 to pi, the set 1 cosine 2x, cosine nx, sine 2x, sine nx is an orthogonal basis. That's part of the reason we don't use powers, that we use cosine nx. Basis for the subspace W of trigonometric polynomials of degree n or less. All right, so I'm not going to prove this statement. I'm just going to say it just follows from computing the following things. The integral of cosine kx is 0. Integral of sine nx is 0 if you do from 0 to 2 pi. If you take mixed products of cosine kx, cosine nx, you get 0. If you take cosine kx, cosine nx, you get 0. Sine kx, sine nx, you get 0. So any combination of two different functions here, if you multiply them together and you integrate from 0 to 2 pi, you get 0. That's what orthogonal means in this context. All right, so we have our orthogonal basis. We don't have to create one using Gram-Schmidt. So let's do an example. I want to find the least square approximation for f of x equals x by a trigonometric polynomials of degree 2 or less. All right, so degree 2 or less, that tells us that our basis is 1 cosine x, sine x, cosine 2x sine 2x, and I stopped because I said degree 2, so I'm not going to go further than this. All right, so the projection onto W of f, that will be, I need to take, oh, f is x. Let's put x here. I need to take x1 and 1, 1. That's going to be the coefficient in front of 1. I need to take the inner product of x with cosine of x, and then cos of x. Cos of x, that's going to be the coefficient in front of cos of x. Same thing with sine of x. And then same thing with cos 2x. And with sine 2x. All right, so that's just the theorem that we got in the projection section apply to this orthogonal basis. So let me give these names. This one's going to be A0. So let's start computing A0. I need to find x1. So we said our inner product was an integral, so I need to integrate x times 1. So I get 4 pi squared on 2 minus 0. I get 2 pi squared. So the numerator is 2 pi squared. The denominator is the integral of 1. So that's x. And you get 2 pi. And so that gives us A0. That's 2 pi squared over 2 pi. And I get pi. All right, so the constant term would be just pi. All right, I'm going to look at the two coefficient here. I'm going to compute them at the same time. So I want x cosine kx. So that's the integral from 0 to 2 pi of x cosine kx. If you remember your Cal 2 well, you'll remember if I have a polynomial times a cosine like this, it's going to be integration by parts. I'm going to take u to be the polynomial, dv to be the cosine, du is going to be dx, and v is going to be sine of kx over k. And so I'm getting x sine of kx over k from 0 to 2 pi minus x sine of, sine of kx over k dx from 0 to 2 pi. Now if I plug in 2 pi and 0 into this, I'll get sine of 2 pi k, which is 0, and sine of 0, which is 0, so I'm getting 0. And then the integral of sine is minus cosine. I'm going to divide by an extra k because of either substitution you can think of. All right, so I get cosine 2 pi, that's 1. And cosine of 0, that's 1. And so I get 0. All right, so I don't really have to compute the denominator, so that saves me a couple of integrals. The top is already 0. So that means already we have A1 and A2 are 0. All right, so we have B1 and B2. Let's write them here. So this is B1, this is B2. I have B1 and B2 left to compute. It's going to be very similar to the last computation we've made, so I'm going to skip ahead here a bit. It's the same type of integration by parts. What do I get? I get minus x cosine kx divided by k plus sine kx divided by k squared from 0 to 2 pi. So I've skipped ahead here, and if you plug it in, you should get minus 2 pi on k. It isn't 0, which is good, otherwise this approximation would be very boring, but that means we do have to compute these. So let me compute them in general. I have to compute the denominator, which would be sine kx. So that's the integral from 0 to 2 pi of sine squared of kx. This is again one of the integrals that you learned in Cal 2. Whenever you have an even power of sine, you should use this identity. You just double the angle. And so you get x on 2 minus sine 2kx on 4k from 0 to 2 pi. You plug in 2 pi, you get pi, then 0, and then you get 0 minus 0, so you get pi. All right, so b1 is minus 2 pi over 1 pi, that's minus 2, and b2 is minus 2 pi divided by 2 divided by pi, that's minus 1. All right, we finally computed everything. So you can see it's not super fast, but you can do all of the AIs together and all of the EIs together in this case, so that's nice. But we do have our final answer. Let me write it here. The projection onto W of the function x is, so a0 was pi, and then the only thing that wasn't 0 were the b's, so I get 2 sine of x, and then b2 is 1, so minus 1 sine 2x. So this is the trigonometric polynomial of degree 2 or less closest to the function y equals x. And that's it. I sketched that for you. So here's in red is the function y equals x. And in blue, I put for you the function we actually got, minus 2 pi, minus pi minus 2 sine of x minus sine 2x. And so you can see it is a wavy kind of sign, but it is getting close-ish to the red line. And just to show you what this would look like with more terms. So this in blue here, that's the projection with degree 6 or less. Right. In fact, you could probably rate just from the computation we've already made, since most of the computation had k's in them, you could probably figure it out what the terms were, because it's minus 2k, 2 over k, that's it. So here you would have y equals pi minus 2 sine of x minus sine of 2x minus 2 sine of 3x divided by 3, and so on. So let's write it that way, that makes it clearer. All right, so let's write what we've learned from all these computations. Some of these computations you don't have to do every time because they're always the same. So the least square approximation of f of x on the subspace of trigonometric polynomials of degree n or less looks like this. And you can see the AIs and the BIs, where A0, so A0, that was the constant term, so you have to integrate f of x dx from 0 to 2 pi, and you need to divide that by, by the integral of 1, so by 2 pi. So let's put a 1 over 2 pi in front. Now, AK was the integral from 0 to 2 pi of f of x cos kx. That's the top, and that's the only part that depends on f. And so that's the only one that you have to do every time. And then we didn't find it, so let me let me give it to you. This 1 over pi, pi is the integral of cos kx squared. We did find it for sine, same thing here for sine case squared, and then f of x sine kx dx. All right, so these are your coefficients in some sense when you're taking projection onto trigonometric polynomials. Let's give this a name, definition 4.4.3. Let f be a function in C0 to pi. Often for this setting, we use periodic functions. The trigonometric functions are periodic with period 2 pi or less in this case, 2 pi, so they will give you at the end a projection that has period 2 pi. And so if you don't start with something that's periodic, it's kind of silly, but it still works, it just doesn't give you the function back. So the numbers a0, a1, b1 are called the Fourier coefficients of f, and the Fourier series is a0 plus ak cosine kx plus bk sine kx. So that's what the Fourier series is, just a projection using a certain inner product on the space of continuous function. All right, so just a few things. As the space of all trigonometric polynomials has infinitely many dimensions, so you cannot project directly on it. So what we do is we project on Fourier series as the limit of the projection on the subspace of trigonometric polynomials of degree n or less. So we limit the degree, and then we have this nice finite orthogonal basis. We find the coefficients there, and then we say, well, let's take the limit, and that's why we get a series instead of a finite sum. So let me say, mathematicians working in harmonic analysis have found sets of conditions on a function f of x, including the fact that it's periodic, that ensures that this Fourier series actually gives you the original function. All right, and that's super helpful in different sections of math and even in music. It's very helpful because these functions have nice behavior in differential equations.